Okay, let's yes. So we took last lecture 4 main concepts. The first one is the energy band diagram. Okay, and we see that, for example, for the for conductors like metals, for example, you have at 0 Kelvin. This is the valence band. This is the conduction band, and there is no gap in between. For that reason, metals are very good conductors, okay, because electrons can move easily from the valence band into the conduction band and conduct current. So this is conductors, we can say. For semiconductors, we have also the valence band, which is completely filled at 0 Kelvin. We have also so this is valence band. We have also the conduction band, which is absolutely free or empty at 0 Kelvin. Okay, but in between there is an energy gap. Okay, so for any electron to leave the valence band to go to the conduction band and contribute to the current conduction, it needs at least energy equal to Eg, the energy band energy. And finally, for the insulators, we have also the same structure again, but this is pretty big. So this is valence band, this is conduction band, and the Eg here is very big. So it's very hard, really hard. Okay. The second concept that we took also is the current carriers in semiconductors. So we have two carriers. We have the electrons, which is conventionally understood, but we have a new concept, which is the holes. Okay, and we said that holes in the origin, at its origin, it's also a moving of electrons. Okay, but we can model them as moving positive charges in the opposite direction. Okay, and as we say, for example, for these holes, basically, if you have a structure like this, okay, and here a hole, for example, just an electron leaves this bond. So this is at, for example, t equal to 0. At t equal to 1, maybe from a nearby bond, an electron moves and fills this hole that was right here, and leaves another hole in its original place, and so on and so forth. Okay. We also determine or should use the concentration of carriers Ni. Okay, and Ni, as we talk, is 5.2 to the power 10 to the power 15, t to the power 3/2 exponential minus Eg over 2 kt. And we said that T is a degree, the temperature in Kelvin. Eg is a property of the material. Each material has its own energy gap number. Okay, and the K is Boltzmann constant, and T again is temperature in Kelvin. And we said that the material is always neutral. So Ni equal to Pi. By the way, there is nothing called Pi. All of them is as Ni. Okay. And I here means intrinsic. Intrinsic silicon, for example. A silicon without any impurities, without any atoms, or any, without any atoms from another material. Okay. In our context here, this means a silicon without any dopant atoms, like phosphorus. The last thing that we talked about is the doping, which we will start with it in this lecture. Okay. The last concept that we covered also is how to increase the conductivity, and just by looking at this equation here, okay, we can't play with EG. EG is an constant for any material. So EG is a constant for the material. So we can't play with it, we can't change it, we can't control it, but we can control the temperature, of course. So for example, Ni, the electron concentration at T equal to 300 degree Kelvin is equal to 10 approximately 10 to the power 10 electron per centimeter cubed. And at also 300 Kelvin, if you measure the whole concentration, let's call them Bi, okay, you will find it also equal to Ni because the material is always neutral, okay? Neutrality is a nature in any material. You can't find the negative more than positive or the positive more than the negative charges, okay? So these are the concepts that we covered. So at 300 Kelvin, we have 10 to the power 10. For example, if I have an example here, yes, if we increase the temperature to 600 degree Kelvin, Ni would be 1.5 multiplied by 10 to the power 15. So it's increased from 10 to the power 10 to the 10 to the power 15. But of course, this is not an efficient way to make the silicon more conductive, we can say. Okay, we need some effect because you will lose energy. You need a lot of energy. So here we doubled the temperature from 300 to 600. So we need more efficient way, okay, or a cheap way, we can say, to do that, which is doping. So let's revise the last concept that we took last lecture, which is doping. Yes. So we said that this is the last thing that we took last lecture. If we add impurities, atoms other than silicon, for example, like phosphorus, that has 5 electrons in its valence band, valence shell, valence orbital, the last shell of the atom, okay? Phosphorus will do something like this here. So each phosphorus atom will make a covalent bond with the surrounding 4 silicon atoms, and there will be a loose electron, we can say. Electrons that can easily contribute to the conduction of current. And how can we envision this with energy band diagram? We said that the phosphorus atoms will add here a new energy level, okay, a new orbital, we can say, a new shell, that the electrons can reside and, you know, go around the material or whatever. And this orbital is very close to the conduction band. So an electron can easily leave the phosphorus atom and go to the conduction band of the total material now, which is a mix of silicon and phosphorus. And once it goes to the conduction band, it can contribute easily to the current. So current, the electrons now in the conduction band has 2 sources. The first one is the phosphorus atoms, and the second one, which is the normal way, you know, the from other silicon atoms, okay, in the valence band, which and at room temperature they can acquire some energy equal to or larger than Eg and go to the conduction band. Okay, and we said that even if we do that and we increase the concentration of the electrons, we still have neutrality. We still have positive charge equal to negative charge. So what is the negative charge density right now? It's still N, but we will call it N, not Ni, because Ni means intrinsic silicon. This is now not intrinsic silicon. This is called extrinsic silicon or extrinsic semiconductor. It's not intrinsic anymore. Equal to the positive charge density. And what is the positive charge? We have originally B, the whole concentration, and the concentration of the new added atoms, the phosphorus atoms, okay? And why these phosphorus atoms has a charge, positive charge, okay? Because each phosphorus atoms contribute an electron to the conduction band, and since it loses an electron, it becomes a positive charge. The number of protons is more than the number of electrons. So each phosphorus becomes a positive ion. But they don't contribute to the current. What only contributes to the current is the carrier that can move. Ion phosphorus can't move. They are very heavy. So in total, we have N equal to B plus ND. But what from this equation, only those guys can contribute to the current. And especially in this kind of material, or with this kind of doping, current mostly will come from N. Basically, N is larger than B. So based on this equation, N should be or must be larger than B. Okay? Because, for example, 2 is equal to 1 plus 1, right? So 2 is, in fact, larger than 1. So from this equation, we knew that the donor atoms, which is phosphorus in that case, and why we call it donors, because they donate an electron, okay, will increase the density of the electrons in extrinsic semiconductor. Okay, so this is the N doping. We can also do another type of doping, which is doping with atoms that have three electrons in their valence orbital, last shell, like boron, for example. So here we will add atoms to silicon with 3 electrons in their valence shell or band or orbital, whatever you call it. Okay, like boron. Boron atoms. So what will happen? Again, something similar to phosphorus. We will have something like this. Very interesting. So silicon here, silicon here, silicon here, and silicon here. Since this guy has only 3 electrons, one of the bonds will be incomplete. There will be a hole there. So we created a hole. Okay, so this is similar to what happened with B, but with phosphorus, all the bonds will complete and there will an extra electron. Here, 3 bonds are complete, but there is one of them is incomplete. Okay, and this means that we have a hole here. So, for example, at T, if this is at T equal to 0, for example, then at T equal to 1, maybe an electron here come and fill this gap, and you will have, a generation of holes in that case. How can we envision this to our energy band diagram? Simply, this is our energy band diagram. This is our valence band. This is our conduction band. And what the boron atoms will do, also something similar to phosphorus. Phosphorus adds a new orbital close to the conduction band. Boron will also add a new energy shell or orbital, but close to the valence band here. Okay? So any electron here can leave the valence band and go to this new orbital. Electrons lives in orbitals. That's a fact. Okay? So basically in intrinsic silicon, they can't be anyhow in the energy band. I'm sorry, yes, in the energy, this in energy gap. So. But now since there is a new orbital here, then a new home, we can say, a new place to go, we can say. So any electron with this very small energy, because the difference between this new orbital and the last shell here in the valence band is very small, just like the phosphorus case, can acquire with less energy, can move from the valence band to this new orbital, credit orbital here, based on the boron atom, and leaves behind the hole. And this hole, of course, can contribute to the current. Okay? So holes now has two sources as well. This is the first source from electrons that moves from the valence band to the newly created orbital, and also due to the original one, which is electrons moves from the valence band to the conduction band. Okay? And again, the material is neutral. This is basic principle. The concentration, or even the number, if you talk about absolute numbers, the concentration of the negative charge should equal to or must equal to the concentration of the positive charge. What is the positive charge in this case? The positive charge is the holes. What are the negative charges here? We have the electrons, and we have also the boron atoms, which we will call acceptors. Why we call them acceptors? Because when electron, for example, in this case, moves from this location to this one, so this guy here acquires a new electron, okay? And so the number of electrons in the boron atom now is larger than the number of protons, most of protons in the boron atom. So the rated charge in the boron atom is 1, or minus 1, I'm sorry, minus 1 electron. Okay? So the boron atoms will act as a negative ion. So this is boron negative ions. Okay? And again, B, based on that equation, must be larger than N. Because it's equal to N plus something. Okay? So it must be larger than N. So we could increase the concentration of holes in the semiconductor. And since we increase B, we call this guy here, or this type of semiconductor, extrinsic semiconductor, we call it B type. So the previous one was called N type because we increased the concentration of electrons N. And here, since we increase the concentration of holes, we call this B type semiconductor. B-type semiconductor. So what else do we have here? Okay. Let's go to another topic. Now, another concept that relates everything together now is that Ni, you remember Ni is equal to 5.2 10 to the power 15 T3 over 2 exponential minus Eg over 2 kT. Ni, the intrinsic concentration, is independent of the doping. Okay? So Ni is always constant. Ni is always constant, of course, at the same temperature. Okay. There is a famous proof that says that N multiplied by B equal to Ni squared. Okay. So this is, if you revise or review some solid state textbook, you will find this famous proof that Ni squared equal to Nb. In intrinsic, this is very, this is very easy. In intrinsic silicon, we have Ni and we have Bi, and Ni equal to Bi. So Ni multiplied Bi is equal to Ni squared or Bi squared. Okay, so it's very intuitive. But with this new information here, or fact, that Ni is independent of doping, that means that in general, N multiplied by B is equal to Ni squared, which is constant. In intrinsic silicon, N equal to B equal to Ni. This is very intuitive. In extrinsic N-type silicon, still N multiplied by B equal to Ni squared. This has a proof, okay? It's not our topic now, but we can imagine it. Basically, what happened, we said that in N-type, if you remember, N increases and at the same time B decreases. Okay? So, they cancel each other. So the multiplication is still the same. N multiplied by B equal to Ni squared. What is N here? N is the concentration in this equation. N is the concentration of electrons in N-type silicon. And B is the concentration of holes in N-type silicon. So simply just to differentiate things from each other, since we call in intrinsic silicon Ni and Bi, we will call this Nn and Bn. So N subscript N multiplied by B subscript N equal to Ni squared. In B-type silicon, we have also the same. N multiplied by B equal to Ni squared. But this is now the opposite. N decreases, B increases, so again they cancel each other. So the multiplication is still the same, Ni squared. And since this is a B-type silicon, we will call this NP, N subscript B, and this is BP, or P subscript B, just to differentiate. So what is NB? Whole electron concentration in P-type silicon. Nn, electron concentration in N-type silicon. What is Pn? Whole concentration in N-type silicon. What is Pp? Is whole concentration in P-type silicon. Okay? So, okay. So basically, N multiplied by B equal to Ni squared. Let's have an example, okay? So assume that you have a silicon doped. So this is let's have example. It's example in the book. This is very good one. So let's have a silicon doped with 10 to the power 16 phosphorus atoms. Okay? Find N and B concentrations at T equal to 300 degree Kelvin. Okay, so the solution. Since he said that T equal to 300 degree Kelvin, that means it's room temperature. So Ni is equal to 10 to the power 10. Just, you know, keep this in your mind all the time. In the exam, of course, I will give you the constants. But of course, you can calculate it easily from the equations that we just mentioned, you know, in the previous topic. Okay. So let's do, there are two solutions here, and both will give you the same answer, of course. So there is the approximate solution, and there is the exact solution. So what is the approximate solution says? There is a fact here is that when we add donor atoms with concentration between 10 to the power 15 to the 10 to the power 17, the majority, or since it's a donor, yes, the number of electrons, okay, will mostly equal to the number of, or the concentration of the donor atoms. So basically, first thing here, since it's B, so this will be N type. Because phosphorus has 5 electrons, it will make a covalent bond with 4 and leave 1 electron free. So it will be N type semiconductor. Okay. In the approximate solution, we can say that N approximately equal to ND. What's ND? The concentration of a donor atoms, which is phosphorus. And in that case, it's 10 to the power 16. And since this is in an N type, so we'll call this NN. NN. And since NN multiplied by BN is equal to NI squared, so Bn is equal to Ni squared over Nn, 10 to the power 20, because this is 10 to the power 10 basically, divided by 10 to the power 16, 10 to the power 4. So this is, you know, a good example to show that N will increase, B will decrease, the multiplication is still the same. So here Nn, in conclusion, equal to 10 to the power 16. Bn is equal to 10 to the power 4. So when we dope a silicon with donor atoms, the concentration of the electrons will increase, the concentration of holes will decrease. Okay. Basically, some of the new added atom electrons or created electrons will fill the holes that was originally in the intrinsic silicon. That's why it decreases. Okay. And in that case, we call Nn the majority concentration, majority carrier concentration, and we call this, of course, minority carrier concentration. Any questions so far? Any questions? We're good to go. Now, this is the first solution. Based on the first solution, we know that Nn equal to 10 to the power 16 electrons per centimeter squared, cube, and Bn is equal to 10 to the power 4. Now let's try the exact solution, not the approximate one. This should be close, right? So let's add a page here. Let's move it. Yes. And copy and paste as usual. Don't have time. And just dash continue. Okay. And the view would be rural lines. Good. So let's continue. Now the exact solution. In the exact solution, we will solve equations. Okay? So what are the equations that we have? First, we have the neutrality equation, n equal to Pn plus Nd. The positive equal to the negative. Positive charge equal to the negative charge. What are the second solutions that we took? That Nn multiplied by Bn equal to Ni squared. Remember, the unknowns here are Nn and Bn, those guys. So we need two equations, right? And these are the two equations. But of course, they are non-linear. So we need to do some combination. I'm sorry, I forgot something. So let's set the size to A4. Yeah. Good. So when I print the lecture, it will be more convenient for your eyes, okay? Because it will be just an A4 paper. Okay, let's go back. So these are the two equations in two unknowns, and we're gonna solve them together. From here, Bn equal to Ni squared over Nn. So let's compensate here. So Nn equal to Ni squared over Nn plus Nd multiplied by Nn. So we have Nn squared minus Nd multiplied by Nn minus Ni squared equal to 0. This is an equation, a quadratic equation with one unknown, okay? And now we know the givens here. So this guy is 10 to the power 20 because it's squared, and this guy 10 to the power 16. Okay. Now by solving this, we're gonna get our answer. Now I'm giving you 1 minute, okay, 2 minutes to give me an answer for this. Okay, I will not do it. Just do it yourself and give me the answer after 2 minutes. Do it using, the equation, which is n should be equal to minus b plus or minus b squared minus 4 ac over 2a, and a is equal to 1, b is equal to minus d, and c is equal to minus 1. Solutions?
still doing the math on it.
You can use MATLAB, you can do it yourself by hand, it will be difficult. You can use calculator, whatever. It's an easy one. Online, there are many websites that you can solve quadratic equations. Any solutions?
Uh, 10 to the 20th power.
What is NN? Oh, sorry, just, oh. What is NN?
10 to the 20 power.
No, that's one. Should give you the exactly the first
10 to
answer.
the 16.
Right. Yes. And of course, if you compensate in here, you will give Bn equal to 10 to the power. Just do it again. Do it again yourself after the lecture, no problem. Okay, this is not an assignment or something. But I wanna convince you that the approximate solution is what will give you the exact solution without making all such complications of solving, you know, quadratic equations or nonlinear equations together. Okay, that's my point here. Okay, but do it yourself. Okay, there are many websites, online websites, using your calculator, even some apps on the phones, smartphones. Okay, you will find the answer is N concentration is 10 to the power 16. B concentration is equal to. I'm sorry. Yeah, after this, you of course you will compensate in this equation, and you can calculate Bn. It will be 10 to the power 4 whole to per centimeter cube. Okay. Of course, here's if we look at this equation here, is one solution is not valid because minus B minus this guy here will be a minus, and of course we don't have a concentration with minus, so it will be minus B plus only. This is the only acceptable solution over 2A. Okay. Okay, that's. But there is a caveat here. Okay. The approximate, let's write it here and write it properly. Caveat. Approximate solution, which is very useful, is valid for, we can say, low temperatures. Okay, and we will see examples afterwards. If you increase the temperature to, for example, 600 to 800, the approximate solution will be wrong, and you should go back to the original or the exact solution. Okay, so let's do that. I don't know if it should be in the same or yes, effective temperature. Okay. So effective temperature on extrinsic silicon, okay? So at room temperature, as we see right now, as an example, we see right now at room temperature, adding 10 to the power 16 phosphorus atoms or donors will convert the silicon into N-type silicon with electron concentration 10 to the power 16, hole concentration 10 to the power 4. Very nice. Now, what will happen if we increase the temperature? So let's have an example. So the same example that we just solved, okay? Again, silicon doped with phosphorus at A 300 degree Kelvin, B 600 degree Kelvin, C 800 degree Kelvin. So calculate NN and BN at those three temperatures. So at T equal to 300 degree Kelvin, we just solved it using the approximate solution and the exact solution. It was very nice. NN equal to 10 to the power 16, Pn equal 10 to the power 4. Now let's do the T equal to 600 degree Kelvin. We doubled the temperature. It's very strong heat. We'll do both, the exact and the approximate. And we're gonna see the difference now. So with the exact, I'm sorry, with the approximate solution, we said that Nn approximately equal to Nd, in that case 10 to the power 16. And we know that Nn Bn equal to Ni square, but now since Ni is dependent on the temperature, we can't put here Ni equal to 10 to the power 10. We should recalculate Ni. And we know that Ni equal to 5.2 10 to the power 15 T 3 over 2 exponential minus Eg over 2 kt, you know, do all that calculations, and that will give you Ni equal to 1.5 10 to the power 15. So this is very strong, you know, or very strong potential for a mistake, that you're gonna assume that Ni is 10 to the power 10 each time. No. If it changes the temperature, Ni will change. And it changed dramatically. It increases 100,000 times, or more than 100,000 times, from 10 to the power 10 to 10 to the power 15. Now let's calculate Bn. It's equal to Ni square. Yes. So 1.5 10 to the power 15 square over this guy here 10 to the power 16. And what it is, it will give us
Excuse me.
225 10 to the power 14. Okay. And just by looking now, look at how the change in Bn. If we accept the approximate solution, and in that case it's a little acceptable. I will show you now. But if we accept it, let's see the difference between Nn and Bn in both cases. At 300 Kelvin, this is 10 to the power 16, this is 10 to the power 4. It is 1 trillion times big, the Nn is 1 trillion times bigger than Bn, or times Bn, 1 trillion. But here, it's around what? It's 10 to the power 16, this is 10 to the power 14. It's around just 50 times. So, if we increase the temperature of an extrinsic silicon, it gradually converted from intrinsic into intrinsic again. Because of what? Because a lot of heat will make more electron hole generation. So more electrons will leave the bonds. Okay. So both sides will increase. N will increase and B will increase. But since N is originally large, very large, 10 to the power 16, the added extra electrons will not affect this number so much. But since in the B case, B was originally very low, 10 to the power 4, and now we will add more holes to it, a big chunk of holes. So this big chunk of holes will affect so much, this concentration will increase it so much. So we're gonna see the effect more in the BN, or minority carrier concentration in that case. So this is the approximate solution. Let's do the exact solution and see the difference. In that case, there will be not much difference. So with the exact solution, if we do it, we will reach the same equations that we just saw in n square minus nd multiplied by nn minus ni square equal to 0. Okay, we know nd 10 to the power 16. Ni, remember again, it changed to 1.5 10 to the power 15. If we solve this guy here, this equation, we'll find that nn equal to 1.022 10 to the power 16. And if we compensate, Bn will equal to 2.2015, 10 to the power 14. There is a difference. It's a little difference, but there is a difference. But now let's do the 800, and we will see a dramatic change here. Let's do it, for example, with red. So C T equal to 800 Kelvin. Approximate solution. Nn equal to 10 to the power 16. If we change, I didn't do the calculation for Ni here. I'm sorry, I didn't write it down. So, so looks like I missed it. I missed the solution. 10 to the power 16. Let's do very quick Ni and see. I maybe have a problem in this, but let's do it. So Ni is equal to, let me calculate it very quick with you right now. Where is my mouse? Yes. I will calculate it with you right now, guys. So 1.5 multiplied by 800. 3/2 multiplied by exponential EG. It's a little bit complicated because, that's fine. So I will give you the, so you do it yourself, okay? So be in here. Do it yourself. Okay? But the exact solution will give us the following numbers. 4.05 10 to the power 16. I'm sorry, this is Nn. And Bn equal to 3.05 10 to the power 16. It's a dramatic change. And we can see clearly the difference between the approximate solution and the exact solution. Although we didn't calculate Bn because we need to calculate Ni. I didn't write down the value of Ni at this temperature, but that's okay. But we can just see the difference even at Nn. So Nn here is 10 to the power 16. Here it's 4. I'm sorry, this is 16 also. 4 multiplied by 10 to the power 16. So it's 4 times less, right? So the approximate solution is not valid all the time. This is the first conclusion. The second conclusion, which is more important in that case, look at these two numbers. This is 4 10 to the power 16. This is 3 10 to the power 16. Just ignore this constant. Just look at this. 10 to the power 16, 10 to the power 16. Right? So it can be approximately intrinsic silicon. So a lot of heat can convert an extrinsic silicon or semiconductor into an intrinsic silicon or semiconductor. Intrinsic semiconductor. Okay? So these are the two important informations that we took, or conclusions that we took from this example. The difference between the exact solution and the approximate solution, and the effect of temperature on the semiconductor, type. If it was any type at 300 degree Kelvin, but it converted to almost intrinsic at 800 degree Kelvin. Okay, that was good. So let's go now to another topic. Any questions far? Any questions? Don't be shy again. Okay, don't be shy. I know virtual learning or online is very bad, even for me. I don't like it. If we are in a classroom, I will see some people yawning, some people sleeping. Some people, just wondering. So I will know just by looking who is understanding very good and who is not, who is follows and who is not. So I can, repeat even without asking you.
So when it comes to the exact solution, we're going to be using the quadratic equation to be figuring it out, and
Yes.
with information to plug it in and figure out the exact.
That's actually it's quite easy. It's not a big deal if you have a calculator, or even a smartphone. You just can download some app, a calculator app, and can do it yourself. It's very easy.
Yeah, it doesn't seem too bad, honestly.
Yes. But just a caveat here, the NR, the intrinsic doping, it changes with temperature. So don't plug each time 10 to the power 10. No. You need to recalculate it at each temperature, at any, if the temperature changes. It's only 10 to the power 10 at T equal to 300 degree Kelvin. Okay? Okay, semiconductor currents. So till this moment, we see that the conductivity in semiconductors is different from normal conductors that we usually we're dealing with in one way, which is the carrier of the current. So in metals we have one carrier, electrons. Here we have two carriers. We have the holes and we have the electrons. Okay? And both have a big contribution to the current. And we will show this right now here. Now, when we study the currents inside the semiconductor, we will also find another, difference between semiconductors and metals, because there are here two currents. There is the normal one, which is called Drifty Current. So the current that you guys were dealing with all the time in circuit theory or whatever, it's called Drifty Current. And what's Drifty Current means? It's a current that came from an electric field. So where is the hell this electric field was? We always take, a circuit, we have a battery, for example, we have a resistor, we have a conductor. There was no electric, no, there were electric field. So electric field came from a potential, a voltage. This potential or this voltage will create electric field on the resistor, for example, so the current can move through the resistor. Okay? And this is called drift current. So the first kind of currents that flows through semiconductors is called drift currents. And basically what's happening, so let's go to the ideal world. Let's change the free space. This is not the semiconductor yet. Here we will talking about electron in free space. How the electron will behave if we apply or exert a potential or voltage or electric field on that electron. So assume we have two plates, right, like this. This has a positive voltage, this has a negative voltage. And we have electron in between. This is just the free space. So we have two plates like this and just a vacuum in between. If you have a voltage like this, then you have electric field. We will call it epsilon, big epsilon. In the book, it calls, the Razavi's book, it calls it E, capital E. We will deviate from this symbol because we see energy band diagram and we have EG, you know. So E in our course is for energy. Field is epsilon or epsilon, whatever. Okay, big epsilon. So if you have a potential, a voltage, positive and negative, you will have an epsilon like this, an electric field. Always the electric field come out of the positive charge, the positive plate, and go into the negative charge. Okay, so it's always going from positive to negative. It's a fact that if you have electric field, if you have electron in an electric field or surrounded by electric field, this electric field will exert a force on that electron. So there will be a force equal to the charge of the particle, here it's electron, multiplied by the electric field. And the force is usually in the opposite direction of the electric field. So this is a vector equation here. This means the force will be in that way. So the electron will be pushed against the electric field. Okay? And a force means M multiplied by A. M is the mass of the electron, and this is acceleration. Wow, there is acceleration. So there is a force, and this force will make the electron to move, and it also accelerate, equal to minus Q epsilon. And the A is equal to dV by dt. What is acceleration? Acceleration is just the change of the velocity with time. So M dV by dt is equal to minus Q epsilon. So we can say that V is equal to minus Q over M. Yes, the integral of epsilon dt. If epsilon is constant, which means this is a battery, okay? So V is equal to minus Q epsilon M T. Very nice equation. So we have, so if you have a free space and you have electron in this free space, it will exert a force on the electron. The electron will move freely in the electric in this field, okay, but in opposite direction of this field, okay, with some acceleration or some speed that it changes with time, and everything is okay. This is in free space. The bottom line here is that electric field electron will move. But in a material like semiconductor, it will be quite different. Now, inside a material, things are very different here. So if you have a material like this, and you have also a potential like this, there will be electric field still. But when the electrons move in a material, it's not a free space. There is atoms there, silicon atoms. There are holes that they can recombine with. There are positive ions, like for example, the phosphorus atoms, which donates electrons. All those guys affect the electron motion. So it will not be straightforward like this here, straight line, no. It will be something, random, but in one direction. So for example, it will move like this, something like this. May go a little on. So if these are vectors and you combine them to each other, trying to add them to each other, you will find a net. You will find some net velocity in that direction. Just like this guy. Okay? So why it moves in that way? Because of basically two reasons. There are many reasons, but basically two reasons. Let's go back to our colors. So this, this distraction, we can say, of electron movement, motion, is because two major reasons. The first one, if the sample, for example, is in room temperature, all the stuff inside the material will gain energy, thermal energy. So atoms will vibrate. Electrons will move, okay? So electrons can collide with each other. Electrons can collide with vibrating atoms, okay? So all such stuff, due to the thermal energy, can cause a deviation. The second major reason is the positive, or the ions. Let's call it ions deviation. So if you, for example, if in any type material, you have these phosphorus positive ions. So let's assume that there were electrons moving like this in a straight line, okay? But when it reaches close to the positive ion here, since there will be attraction force, it may deviate like this. This is what I call deviation. You can call it whatever, I mean, it deviates from its original course. Okay? That's what I meant by deviation. So that's why the motion here is not, perfect motion like a free space. It's like this, it's distracted all the time. But there is a net direction, for example, you can say, resultant, of a current in certain direction. Okay? So this is how electrons will move inside the material. Now, we need to know like what we did here, calculated the velocity. We need to know now what's called V drift. This is also V drift, okay? But let's stress the naming in that context because we will see another type of currents afterwards. So V drift. So actually V drift is very simple. It is proportional to the electric field applied. So notice that when you have relatively small electric field, okay, the motion is just the velocity of the electrons is just linearly changing with the electric field, and the proportionality constant is called mu. This is called mobility, and that depends on the material. So each material has its own mobility constant, and also depend on the carrier. So there is mu n and there is mu b. So Vn, the drift velocity of the n carrier, the electrons, is equal to minus mu n multiplied by the electron. Why minus? Because you move in the opposite direction. Just like look at here. So it's minus e. So this is vector and vector. And Vb, mu b epsilon as well. Okay? So this is the drift velocity we have. Okay? So, yes. One last thing here is that usually, we need another page. Yes. So we said that this is dependent on the material and the carrier type, either hole or electron. So in silicon, for example, mu n is equal to, let me write down the numbers, 1,350 centimeter squared volt second, and mu b is equal to 480 centimeter square volt second. Oh wow! So we notice that mu n is larger than mu b. It's actually very larger than mu b. It's three times, almost 3 times. And this has the reason. And the reason is the mobility of electrons is larger, which means that they have larger velocity under the same electric field because they move in the conduction band usually, okay, which is, just free. Most of the orbitals there are free. But the mobility of holes actually happens in the valence band, which is completely filled, of course, at 0 degree, or partially filled at room temperature. But it's more filled than the conduction band. And the mobility of holes, remember, it needs an electron to move from one bond to another bond. So it needs some energy to leave this bond, then go to another bond and fill it. So it's a little bit complicated, more complicated than the movement of the electron in the conduction band. That's why the mobility or the speed or the velocity of electrons is larger than the velocity or the mobility, we can say, of the holes. Okay. So next time we will continue after this point. Okay, we'll calculate the drift current. We'll calculate the conductivity or resistivity, just like any material. Okay, the rho, if you remember, or sigma, the conductivity or resistivity of the semiconductor. And also we're gonna demonstrate another type of current called diffusion current. This was a drift current. We'll see another type of current called diffusion current. So do you guys have any questions so far in any part of the lecture? Any questions?
This part makes sense.
Makes sense?
Different numbers. I got different numbers for your 600 and 800 Kelvin examples that you had on a previous slide. I got different numbers. I just wondered how you got to your numbers.
Those numbers? You mean those numbers?
Yes.
Just plug in this equation.
and I got different numbers.
I can double check with you. This is my solution, by the way. So I can double check again the numbers with you after the lecture. Okay. You made it electronically, or you made it yourself by hand?
With a calculator.
Okay. So let me do it again. That's fine. Let me do it again and double check. Okay. We can also you can also call me or whatever, you know, tomorrow or something to double check. If I just get the same numbers again and again, I will double check and triple check. Okay. I will email you with my results.
Okay. Like if I send you a picture, or if I scan a page with my work and you see what went wrong.
Of course,
I'd appreciate it.
Of course. But the conclusion will not change. Okay. As we increase the temperature, the doping will we can say changes. So the N-type material will not all the time will be still in N-type material. The minority concentration will increase, and at some point they may be equal to each other. Okay. So the basic conclusion are facts. These are facts. Okay. Whatever the number is, these are facts. Okay. Any other questions?
What's the homework?
I will publish it. Okay. I didn't decide yet on homework. I will choose some example from the book and send it to you. Okay. Over Canvas. Okay.
Okay.
Okay, guys. Thank you very much. If you have any question, next time you can stop me before starting the lecture. Okay. And see you next week. Bye-bye.
Right. Thank you.
Thank you very much.
Yeah. Thank you.
Thank you. Thanks very much, I want to say.
Thank you.
Have a